let's continue our study of rings, and I want to start off here with a definition. This is really some terminology, so let's start off with a ring. So let's let R be a ring. And there's two parts of this definition. So the first part, if little r times little s equals s times r for all little r and s in capital R, then we say R is commutative. Right? So remember, rings have two operations, and by definition, the addition operation is commutative, right? R with respect to plus is an abelian group, right? But there is no such condition built in for multiplication, right? So sometimes when you multiply two elements of a ring in two different orders, you can get two different answers. In the case where no matter which two elements you multiply, you get the same result in either order, then we say that we've got a commutative ring. We say that R is commutative. The second part here, if capital R has a multiplicative identity, right? So okay, so then capital R is a ring with unity. And the typical, the usual symbol, so in this case, the multiplicative identity, we refer to it as the unity element, or as unity. So multiplicative identity is denoted by the symbol 1, right, called unity. So what I want to point out here, this is not necessarily the number 1, right? It is the symbol we use for the multiplicative identity in whatever ring we're working with, right? So this generically, we use the symbol 1. So, for example, Z is a commutative ring with unity. Of course, we know when you multiply two integers, it doesn't matter what order you multiply, and the number 1 is the multiplicative identity. Right, and so Z is a commutative ring with unity. Next example, let's look at M sub n Z. This is a non-commutative ring, right? When you remember, this is the ring of matrices with entries in the integers, right? When you multiply matrices, you may or may not get the same answer when you multiply in different orders. So this is a non-commutative ring with, now how about unity? In this case, the multiplicative identity is the identity matrix, right? The matrix with zeros everywhere off of the diagonal and ones along the diagonal. So with unity, I should put some dots here, dot, and zeros, these are giant zeros, right? So ones along the diagonal, zeros everywhere else. This right here is the multiplicative identity inside this ring right here. Another example, if n is greater than or equal to 2, then nz is a commutative ring without unity. Oh, one more example here. So let's let R equals 0. And here, I don't mean the number 0. I just mean the symbol 0. Right? Just take ring R that has a single element. So yeah, so in fact, let me say this. So that is R is, I want to say a ring consisting of a single element, right? So, I mean, a ring always has to have an additive identity, so I'm using the symbol 0 here, right, to stand for that, but I don't necessarily mean the number 0. So this is a single element with operations. Well, there's not a whole lot possible here. When you add 0, you got to get 0, and when you multiply 0, you got to get 0. Then R is a commutative ring with unity, but in this case, the unity element is actually the 0 element. Right? So the element that behaves as a multiplicative identity has to be the only element that's in there. And this has a name, so let's say comma, called the 0 ring or trivial ring. Now, I'll make a couple of observations. So the first one, so let's start off with a ring with unity. So let R be a ring with unity. The first observation, so suppose that there's more than one element in our ring. So suppose that R, it's always got to have an additive identity 0. So suppose R minus that element is non-empty, right? So there's somebody in our ring other than just the identity. Sorry, I can't read my writing here. Oh, pick. Okay, so let's just take somebody. So let's say pick little r. I don't want it to be equal to the 0 element, so let's pick some non-zero element in R. Now, suppose that 0R is equal to R. In other words, suppose that 0 behaves as a multiplicative identity. Now, from what theorem was this? I want to say 18.1. Let me just check it over real quick. Yeah, 18.1. 0. So from 18.1, what we know that 0R has to equal 0. That was part A of theorem 18.1. And so R has to equal 0. But wait a minute. We just said that R is not equal to 0, right? We picked it in here, so this is a contradiction. So a contradiction. And so what that tells us, all right, so let's write down a conclusion. right? We started off with a ring with unity, so we know that there is somebody that behaves as the multiplicative identity, right? And what we said is, suppose that that multiplicative identity is actually 0, right? The additive identity. We got a contradiction, and so let me write this nicely. So conclusion. If R is a ring with unity and has more than one element, then 0 is not equal to 1. Maybe that looks kind of silly, right? But what this is saying, remember, these are not numbers necessarily. What this is saying is the additive identity and the multiplicative identity are distinct elements. They can't be the same. And, right, so there's the first of the observations. Second of the observations, so suppose that 1 and 1 prime are multiplicative identities, or are unity elements. What we're saying is, suppose that we have a couple of different unities, and obviously we're going to show, I think you can expect, what we're going to show is that they actually have to be the same. So then 1 is equal to 1 times 1 prime, right? Because 1 prime is an identity element. When you do 1 prime times 1, you have to get 1. But also, 1 is unity, so 1 times 1 prime has to equal 1 prime. All right, so what does that tell us then? It tells us that unity is unique. So, conclusion. The unity in R is unique. All right, so similarly, similar to what we know about in groups, right, where the identity element is unique, now we have that the unity element is unique. So some more examples. Now, yeah, let's let R1 up through R sub n be rings. If each R sub I is commutative, then when you look at the direct product R1 cross ... Rn, this is commutative. Right? So remember, if you have a bunch of rings, you can take the direct product, you get a ring, right, using the obvious operations. And so what we have here is a direct product of commutative rings is commutative. If each R sub I has unity, then, then the direct product will have unity, and it will be unity from R1, comma, unity from R2, comma, unity from R3, and so on. So I'm just going to write it like this: 1, comma, 1, comma, ... comma, 1 is unity in the direct product R1 cross ... Rn. And here, be careful, I do not necessarily mean the number 1 here, right? That first 1 right here is unity in R1. The second 1 right here is unity in R2, and so on. So, just kind of following up, still part of this example, I guess. So, Z3 cross M2 Z is a non-commutative ring, but it does have unity, and the unity is going to be the number 1, comma, the identity matrix, right? That's unity in Z3, that's unity in M2Z. And let's say 3Z cross Z, here's a ring, it's commutative, but it doesn't have unity because 3Z has no unity. So this is a commutative ring without unity. Some more terminology here. So let's let R be a ring with unity, and there are times when we need to insist that we're not talking about the trivial ring, right? If you write down, sometimes you write down a statement and someone will say, but what about the trivial ring? Yes, fine, okay. But so when we want to insist that we're not talking about the trivial ring, this is often how we'll do it. Let's take a ring that has at least 2 elements, right? It's got a 0 and it has unity not equal to 0, so it has at least 2 elements. Let's say, and here's our usual notation, R star, right? Remember, in general, that means the set where we delete 0, right? Delete the 0 element. In this case, remember, now when we write R star, what we mean is R minus the identity, right? The additive identity, no matter who it is. It's not necessarily the number 0. If R in R star satisfies this property, has a multiplicative inverse. But that is an element S in capital R, such that, and I don't really need to use, let's go straight, instead of saying S, let's go straight to the obvious symbol, an element which we'll write as an R raised to the minus 1, such that R times R inverse equals unity, which equals R inverse times R. Then we say that little r is a unit. So then R is a unit. So so for example, in Z8, two is not a unit. You can just go through all the elements of Z8. 2 times 0 is not 1. 2 times 1 is not 1. 2 times 2 is not 1. Go all the way through, and what you'll find is that 2 times anybody in Z8 is not equal to 1, so 2 is not a unit. But 3 times 3, that's equal to 1 in Z8. So 3 is a unit. It happens to be its own inverse, right? But 3 is a unit, right? There exists an element such that when you multiply, you get the identity element, the multiplicative identity, the unity element. So this leads to a couple of definitions. So let's let R be a ring with unity. Part A, if every non-zero element, so if every element of R star is a unit, then R has a name. It's called a division ring. So R is a division ring. Part B of this definition. So if R is commutative, and every element of R star is a unit, then R is a field. So what do we have? Starting off with R here, we did not assume that R is necessarily commutative, right? It's just a ring with unity. If every element, every non-zero element is a unit, meaning it has a multiplicative inverse, then we say that R is a division ring. If we add the requirement that R is commutative, right, then we get a field. So another way to say this is that a commutative division ring is a field, or maybe I should say this better. A field is a commutative division ring. So a field is a commutative division ring. In this class, division rings will hardly ever come up, right? They're an object of study, but for this class, it's really not going to come up. Fields are going to come up all the time. It's extremely important. And in fact, Math 483 is essentially the study of fields, right? It's the beginning of, or it's a part of studying fields. Here's a few important examples. So let's see. Q, R, and C are fields. Z is not a field, right? So what do we know? Well, Q, R, and C are rings, and every non-zero element of Q, R, and C, and I should say this a little better, Q, R, and C are commutative rings, and every non-zero element of any one of these three has a multiplicative inverse, right? Just take the reciprocal. However, Z is not a field. It is commutative, right? But the only units in Z are plus or minus 1. Right? So Z is not a field. So here's a kind of quick observation. If R is a field and A and B are non-zero elements, then when we multiply A times B, what we get is a non-zero element. All right, so let's say it like this. So then A, B is an element of R star. And the reason, so let me just write up a quick explanation of why this is true. So reason. If A times B is equal to 0, then if I multiply both sides of this equation, let's say by A inverse, so then we have B equals A inverse times AB, which is equal to A inverse times 0, which we know anytime if you take any element times 0, you get 0. But that's a contradiction, right? Because we said that B was non-zero to start with. So contradiction. And so what this tells us, here's a way to think of this. If you take two non-zero elements of R, you get, when you multiply, you get a non-zero element. In other words, R star is closed under multiplication. And so, as a conclusion, right, so if R is a field, then R star with the operation of multiplication is an abelian group. All right, we showed closure here. We know that multiplication is associative, and then saying that it is a field is saying that every non-zero element has an inverse, which means then that every element has an inverse. How much time we got here? Yeah, okay. Keep going for a little bit. So let's get another definition here. Just as when we studied groups, one of the things we learned about fairly quickly after that was subgroups, right? There's a notion of subring. And so let's let R be a ring. And let's take some subset, so S, a subset of R. If S is a ring under the same operation as we have in R, I should say operations, under the operations of R, then S is a subring of R, denoted with the same stuff or the same symbol right there that we use for subgroups, right? So S less than or equal to R means subring. So for example, um, 2Z is a subring of Z. Right? It's a ring. 2Z is a ring. In fact, NZ is a ring under the operations of addition and multiplication. Right? And so 2Z, in fact, NZ is a subring of Z. Now, just as we had a subgroup test, there's a subring test. So our next theorem is going to tell us how to verify, right? If we've got a subset, it's going to give us a way to check whether we've got a subring or not. So theorem 18.2 is the subring test. So it goes like this: a subset S of the ring R is a subring of R if and only if so two things need to happen. Well, really three things, but I'll state it in two pieces. So first, S needs to be non-empty. And second, for all, call them A and B in S, A minus B is an element of S, and A times B is an element of S. In other words, a subset is a subring if and only if it's non-empty, closed under subtraction, and closed under multiplication. So for the proof, this is an if and only if, so I've got two directions to check here. So in the forward direction, right, we're going to assume that we've got a subring. So let's just say, assume S is a subring of R. Okay, so now what do I need to do? I need to show that it's non-empty. Well, of course it's non-empty. Right, since it's a ring, it has to at least contain 0. Right, so since S is a ring, right, that means that it's got to be an abelian group under addition, which means it's got to have an additive identity. So it's got at least one element. So since S is a ring, we have 0 element of S, and so S is non-empty. So now we need to show that it's closed. So now let's let little a and b be in capital S. Well, since S plus is an, it doesn't matter if it's abelian, I guess, so let's just say is a group, we have that minus B has to be an element of S. Why is that? Because S is closed under inverses. If B is in S, then minus B, its inverse also has to be in S. So now, by closure, right, we know that S is a ring, which means that it's closed under both addition and multiplication. So by closure, we have A minus B, which just means A plus negative B is an element of S, and AB is an element of S. Right? Since S is closed under both addition and multiplication, we know that A minus B and A times B have to be in S. Now for the reverse direction, so let's assume that 1 and 2 hold. Okay, so now what do I need to do? Well, I need to show that S is an abelian group under addition. So assume 1 and 2 hold. We must show that S is an abelian group under plus. Then we'll have to show that associativity holds under multiplication. So let's say it like this. associativity and what else? And commutativity with respect to plus are inherited from R, right? We already know we're in a ring R, and so it's commutative. It's an abelian group with respect to plus. It's also associative. So now, let's see, what do I need? I need closure, and I need an identity. So let's see, right. How do I want to say this? So given A in S, nope, 0, which is equal to A minus A, is an element of S. It now follows, whoops, that minus A is an element of S. And in fact, I should write this, I should do this a little better. A minus A, which is 0 minus A, is an element of S, right? We know that we're closed under subtraction. So first we show that 0 lives in S. Now, knowing that it's closed under subtraction, we know that 0 minus A, which is negative A, is an element of S. So now, to see that S is closed under plus, note that A plus B is equal to A minus negative B. We know that inverses are inside, and so now we see that A plus B has to equal A minus negative B, right? That's an element of S. Right, okay, so then the last thing, so the last thing now, associativity with respect to multiplication is inherited from R, as is, or as are, the distributive properties. So most of this stuff follows from or is inherited from R. So really then, the only thing that we needed to do was to check the group aspect with respect to plus, right? Okay, so that completes the proof. Just give you one quick example here. The set, which we usually write as Z bracket I, consisting of all things of the form A plus BI, where little a and b are integers. This is a subset of, subset of the complex numbers. And so what I want to do is actually show that Z bracket I is a subring of the complex numbers. Right, where here, of course, I means, the square root of -1. Now, okay, so it's definitely non-empty. There's a whole bunch of elements in here. In fact, it's an infinite set. So what I need to do then is show that it's closed under multiplication and subtraction. If I subtract two elements of it like this, of course, I'm going to get something like this. If I multiply two elements that look like this, right, I'm going to get something that looks like this. And so I'm just going to say check, right? You can check the details. So check, or apply. Oh, I guess I'm being a little bit lazy here. I'll do it. Okay. So note A plus BI. I'm actually not being lazy. I have to meet a student in just a second, and so I'm trying to get the entire video recorded before I have to do this meeting. Okay, so A plus BI minus C plus DI, that is A minus C plus B minus D times I. That's definitely in Z bracket I. And then if I multiply A plus BI times C plus DI, that's going to be AC minus BD plus AD minus, plus BC times I, also in Z bracket I. So it's a non-empty set that is closed under subtraction and multiplication by the subring test. We see that Z bracket I is a subring of C. And you should note that this makes life much easier. We now know that this thing is a ring because we showed that it's a subring of a known ring. And that's just like in group theory, sometimes it's a pain to show that something is a group and check all the axioms. The subgroup test streamlines things. Same thing here. Sometimes to show that you've got a ring, it's easiest to show that that object is a subring of some known ring. Okay, so we'll stop here and we'll see you next time.